All right, so we're going to talk about polynomial and rational functions. So a polynomial function of degree n is, we are looking at something that looks like this. It can have a lot of terms in it, but the first term can't be equal to 0. And the coefficient of the variable to the highest power is called our leading coefficient. It's the one that's going to be with the highest degree that's happening in there. Polynomial functions have a positive integer degree. So this one would have a degree of 5. This one has a degree of 6. The difference between these two is that this has each of the parts or the terms of our polynomial function are being added. In this case, our polynomial function is being multiplied. So we have to add the degree of 4 plus 1 plus 1, which will get you 6. These are not polynomial functions because they don't have an integer degree. They have the square root would actually give you a power to the 1/2. And this with a 3 over x squared would actually make that as negative 3x to the negative 2. So it has a negative exponent. So those aren't. Another way to tell them apart is by their graphs. Polynomial functions have smooth and continuous graphs, where non-polynomial functions have sharp corners. They're discontinuous, so they might be sharp like these, or they're going to have gaps in them. The leading coefficient test, as x increases or decreases without bound, the graph of the function eventually rises or falls. For an odd function, it's going to go opposite. If it is a positive, it's going to rise. Think about the stock market rising up, so it's going in a positive direction. If it's negative on your first term, it's going to go down. For the evens, positive, we've been talking about these so far in our lectures, are going to go up, and a negative parabola type situation is going to go down. So the way to figure out what's going on with your degrees and your behavior of your graph is if your degree is an odd degree, then first thing you want to do in both cases, you want to figure out the right side of the graph and then figure out the left side. So if we are positive, we know the right side's going up and the other side of the graph with odd will go opposite directions. So this will be your end behavior. If it is negative, then the right side will go down and the left side will go up. And with your even, if it's positive, they both go up. And if it's negative, it's going to go down. So the even, think about it like even Steven, same behavior at each end. Odd, opposite behavior at each end. And it truly is easier if you choose the right side first and then the left just follows, whether it's odd or even. All right, so let's go look at some degrees. So for example, 1, we have f of x equal to x cubed plus 3x squared minus x minus 3. We have completely separate terms on this. So on this one, we just look for the highest degree. So the degree is equal to 3, which tells us it's an odd degree because 3 is an odd number. And then we need to know what the leading coefficient is. We know that the leading coefficient is actually equal to 1 because there's no number sitting there, so we know there's a 1 there. But what we really care about is that it's positive. Because it's positive, we know it will go up. Because it is odd, we know that it will go the opposite direction. All right, let's look at example 2. If we have f of x equal to x to the 4th minus 4x squared. All right, so our degree is equal to 4, which we know is even, and our leading coefficient, again, happens to be a 1, but what we really care is that it is positive. Positive goes up, even does the same thing, so they both go up. Example 3, we have f of x equal to negative 4x cubed times x minus 1 squared times x plus 5. Now, you're not going to multiply this all out. We're just going to add our exponents. So our degree will be found by adding each of the exponents. So we have 3 plus 2 plus 1. The number's sitting right there. And when you don't see a number, you know that's going to be a 1. So 3 plus 2 plus 1 gets us 6, which we know is an even number. And our leading coefficient happens to be equal to a -4, but what we care about is that it is negative. The negative tells us it will go down, and the fact that it's even tells us that it will go the same direction. Okay, so that's how you're going to figure out the degrees, and you're going to figure out your end behavior for your graphs. Alrighty, next thing we're going to look at is multiplicities and x-intercepts. So the general form is x minus r to the k, where r is the root, k is the multiplicity, and these are basically our x-intercepts on our graph. They're also called roots or solutions. When we look at the multiplicity, which is going to be the k, the exponent that's on the parentheses, an even multiplicity does two things. So even, think about it, 2, because it's an even number, so it will touch and turn. For the odd multiplicity, we think about the number 1 is an odd number. It does one thing. It'll cross the x-axis. To find our zeros, we're going to set f of x equal to 0. Same thing we were doing in previous sections. To find the x-intercepts, y equals 0. And then we'll solve for our x. There are the maximum number of turning points is n minus 1, where n is the degree of the polynomial function. All right, so let's go find some zeros and multiplicities. So we're going to find the zeros and multiplicities. Like how many times does it occur? Basically, you're looking for the exponent. So we are given f of x equal to x cubed plus 3x squared minus x minus 3. This has 4 terms in it, so we are going to split the terms in half and factor by grouping. So in the first half, we have x cubed plus 3x squared. In common, they have an x squared, so we will factor out an x squared and are left with x plus 3. Bring down our negative sign between an x and a 3. The only thing we can factor is a 1, and we'll be left with x plus 3. Now what I want you to notice is the parentheses match. That will happen every time when you're factoring this way. If they match, you did it right. If they don't match, you've done something wrong. All right, so we get 0 equals, we have that common factor of x plus 3, and we're left with x squared minus 1. Now, one of the things that's good to note is that x squared minus 1 is the difference of squares, and it will always factor to be a plus and a minus, or a minus and a plus. The order doesn't matter. Taking the square root of x squared, we get x. Square root of 1 will get us 1, and we repeat. Difference of squares. Or you could just set this equal to 0 and do it that way too. There's a couple of ways you can do this one, but we're going to do difference of squares because it's good for us to know that skill. All right, now what we're going to do is set each part equal to 0. And this will get us x equals -3, x equals -1, and x equals 1. And what I want you to notice is that the exponent for each of those is a 1. That's called our multiplicity. So these are our zeros. And then the multiplicities, and I usually just write mult. So this are equal to 1 in each case. It's all 1 for all of them because of that. Because the multiplicity for each one, and I can write this for each one, multiplicity equals 1, And the multiplicity equals 1 because there's just a 1 on each of those for an exponent on the parenthesis there. That tells us that they are all odd and they're going to cross. And usually I just write crosses. You can write crosses x-axis, but typically we try to write as little as we can. We're working on these. All right, let's go look at another one. So this is one where we had to do a little bit more factoring. Sometimes you don't have to do the factoring. A lot of the factoring will be done for you already, so pay attention whether or not you have to do a whole lot. So example 5, we have f of x is equal to 1/2 times x plus 1 times 2x minus 3 squared. This is already factored out. We don't have to do a whole lot other than set it equal to 0. And then we'll take each. We don't really worry about this because it doesn't have an x on it, and we could multiply both sides by 2 to cancel it out, or basically divide by the 1/2. So we don't worry about that. We only worry about each side of the parentheses. Now, if there was an x here, we would worry about it because then that's one of our terms. So we're going to take our x plus 1 equal to 0 and our 2x minus 3 equal to 0. We won't worry about the 2 just yet. Just take what's in the parentheses. So this will get us x equals to -1. This one we need to do a little bit more work. So x will equal 3/2. So these are going to be our zeros. The multiplicity on this one is equal to a 1, because that's what's up here, right here. Either way you want to look at it. And the multiplicity for this one is equal to 2. That's the only time you're going to worry about that part. All right, so the multiplicity of 1 tells us it's going to cross the x-axis, so crosses. And this one is going to touch and turn around. I usually just write touch and turn. All right, let's look at another one. Example 6, we have f of x equal to -4 times x plus 1/2 squared times x minus 5 cubed. So again, we're only going to take the parts that out of the parentheses. So x plus 1/2 equal to 0 and x minus 5 equals to 0. So x will be equal to -1/2 and x will be equal to 5. The multiplicity here is 2 and the multiplicity here is 3. And again, those numbers are coming from those exponents. So for 2, that tells us it's going to touch and turn around. And for 3, it crosses the x-axis. So it's just about understanding what happens at the behaviors of each of those zeros. So the next thing we're going to talk about is graphing a polynomial function. This will be similar to what we've done in the past. We'll use our leading coefficient test. We'll find our X-intercepts, our Y-intercepts, and use the max number of turning points to check whether it is drawn correctly. Alrighty, I'm going to get a new sheet here to start this next problem. So we have f of x is equal to x to the 4th minus 9x squared. So the first thing we're going to look at is our degree. The degree of the function, because they're separate terms, is going to be 4, which tells us that's an even degree. And our first term, the a sub n or the a or whatever you want to call it, is equal to 1. What we really care is that it is positive. So positive tells us it goes up, even tells us it matches. So we know that our graph will go up like this. Part 2, we're going to find our x-intercepts. X-intercepts, that's where we have y equal to 0. So 0 equals x to the 4th minus 9x squared. We have two terms here, so we're going to look for our greatest common factor. In what they have in common is an x squared. We're left with x squared minus 9. Again, that is a difference of two squares. So 0 equals x squared times x minus 3, x plus 3. Now we'll take each term and set it equal to 0. Well, the x squared equal to 0, we can take the square root of both sides, but it's just going to be 0. And this will be x equals 3, and this will be equal to negative 3. So that is the zeros. Now we got to look at the multiplicity. The multiplicity on this was a 2. The multiplicity on this one is a 1, and so is the next one. So this will touch and turn. This one crosses, and this one crosses. So 0, 0, negative 3, 0, and 3, 0. Because they are x-intercepts, the y part will be equal to 0, which is what we stated. All right, now let's find our y-intercept. The y-intercept is just like we've been doing before, x equals to 0. So y equals 0 to the 4th minus 9 times 0 squared. Well, that's just going to get us 0, so we have 0, 0 as our y-intercept. And then we'll find our max number of turning points. That's the maximum number of turning points in our graph. It does not have to turn that many, it's just the most it will turn. So n minus 1, that's going to be the degree of the problem minus 1. We determined at the very beginning that a degree was equal to 4 off of our equation. So this will get us 4 minus 1, which is equal to 3. So at most we'll have 3 turning points. All right, so let's graph our problem. We again don't have very big numbers, but we have small ones. So we have we're going to plot our x-intercepts. We have 0, 0, negative 3, 0, 3, 0. Our y-intercept was also 0, 0. So I've got our plots pointed. Now, this is why you need to know the end behavior. We know that the end behavior goes up on both sides. So that tells us what's happening with the graph. We know that this part and this part will go that way. Now, let's go over here and look at negative 3, we know that the graph crosses. So it's going to come down. And then at 0, it's going to touch and turn. So I'm just going to loop this up, touch, and turn around. And on the last one, it also crosses. And that's why we need to know the behavior. Now, yes, you can graph this on a graphing calculator, but we don't always have a graphing calculator. And this is good stuff for you to know and understand and be able to sketch a graph without a graphing calculator. I teach this the same way in all of my classes, being able to graph by hand. All right, let's go look at example 8. So for example 8, we have f of x equal to negative 2 times x minus 1 squared, x plus 2. So that's an x minus 1. All right, first thing, we're going to look at our degree. The degree is going to be one where we have to find it. It's 2 plus 1, which will get us a degree of 3, which is an odd degree. And our a sub n, the first term, is negative 2. So that tells us that it is negative. Negative tells us the graph will go down. Odd tells us it goes opposite. All right, then we have x-intercept where y is equal to 0. So we just need to take each part. There's no x on that -2, so we're just going to take the two parts of our parentheses there. So x minus 1 equals 0, and x plus 2 equals 0. X will equal 1, and x will equal -2. On the x equal to 1, our multiplicity is 2. And on the x equal to -2, the multiplicity is 1. So multiplicity of 2 does two things. It will touch and turn. And a multiplicity of 1 tells us it will do one thing. It crosses. Those intercepts will be 1, 0 and -2, 0. Because again, our y is equal to 0. Go find our y-intercept. That's where x equals 0. So y equals -2 times 0 minus 1 squared times 0 plus 2. -2 times -1 squared times 2. That's -2 times 1 times 2, which will get us -4. So 0, -4 will be our y-intercept. We'll find our max number of turning points. Max number of turning points, again, is n minus 1, which is our degree minus 1. Our degree for this problem was 3, so this will be 3 minus 1, which is 2. And just to go back for a second, if you recall, we found on the last one the maximum number of turning points. So that's what's happening. We turn once, we turn twice, and then we turn, you got to be able to see the graph. So here's a turning point. There's 1, there's 2, there's 3 turning points on the graph. It's where it turns. How many times does the graph change direction? All right. So let's go do step 5 and graph it. We again don't have really big numbers. All right, so we have 1, 0, -2, 0, 0, -4. Those are the points that we have. We know that our end behavior, the left side is going to go up, the right side will go down. So the left side goes up, right side goes down. Now at our x-intercept at -2, we discovered it would cross. So it's going to come down, and then it's going to come back up, and it'll go up to the other graph point of x equal to 1, our other intercept, and it's going to touch and turn. And you can see we changed directions once, changed them twice. Maximum number of turning points. So there's our graph. All right, so our most basic rational function is f of x equal to 1 over x. And here we're going to get into what we call asymptotes. So we're going to see how the graph behaves with what's going on. I'm going to switch to the colored paper so we can see it maybe a little bit clearer. So we can see what's happening. This is a basic function, rational function of 1 over x. We can see that the graph, what happens with the numbers is what we're seeing here. And how, when they go together, we end up with a graph that does this and this. Well, what's happening here is there is an asymptote, a horizontal asymptote going this way, and there's a vertical one going this way, where they will increase without bound going up, going this way, coming down, or going this way. But they're not going to cross where y equals to 0 or x equals to 0. There's some notation about approaching from the right and approaching from the left. That's stuff that you'll need to understand more in business math too. So an asymptote is where the graph only gradually approaches or never reaches certain points. They can be vertical, horizontal, or slant. In this class, we're only going to learn about vertical and horizontal. The line x equal to a of a graph of a function is if the function increases or decreases without bound. Just means it just keeps going on to infinity as the x approaches that value of a. So here's an a. That's where we've got an asymptote going. It's going to keep on increasing. It can also do it from this side. It can come in from this way, and it can come in from this way. To find, so a graph may never cross a vertical asymptote, and to find them, it's where the denominator equals 0. This is basically what we've done before of finding the domain and worrying about dividing by 0. A function may have no vertical asymptotes, or it can have several of them. We also will learn about some horizontal asymptotes, but let's go look at the verticals first. Okay, so this will be example 9, and we're talking about vertical asymptotes. I'm just going to call them VAs because there are a lot to write out the words. There's 3 different options that can happen for vertical asymptotes. So if we have f of x equal to x over x minus 3, we're going to worry about the denominator. So vertical asymptotes deal with the valley of our problem. Vertical goes with valley. So the denominator, x minus 3 equals to 0, x will equal 3. And the line, x equals 3, is a vertical asymptote. Another one that we might see is g of x equal to x plus 2 over x squared minus 9. Again, the valley of the problem. X squared minus 9 equals 0. We've talked about this already today. Difference of squares. X minus 3 times x plus 3 equal to 0. So x minus 3 equals 0. X plus 3 equals 0. So x equals 3 and x equals negative 3. So both of these are vertical lines that are vertical asymptotes. So these are lines. These are not points. That's why when we find a point, we want to write it as an intercept, so that we don't mistake those as an equation of a line. These are actually equations of lines. And then the third one again, we're going to take, we have x minus 1 over x squared plus 1. We'll take our denominator, set it equal to 0, get x squared equal to negative 1, and when we take the square root of both sides, we get x equals to plus or minus I. This means there are no vertical asymptotes. So you can have one asymptote, you can have a couple of asymptotes, or you can have no vertical asymptotes. Okay, so the next thing we're going to learn about is horizontal asymptotes. So for horizontal asymptotes, those are the lines that are going to go horizontally, going this way. Now, you can cross a horizontal asymptote. It doesn't typically happen, but it can. And typically in the graphs that we do, it'll go through the origin ones. But it can cross a horizontal. Never a vertical, but it can pass through a horizontal. So in the fraction form with the coefficient and the term in respective places, we're going to use the highest degree. Now some of you might know the n and the m, and if you know that, it's going to be fine. I'm going to show you how to do them using the highest degree to do it, because I think it's easier than trying to remember. You can also know Bobo Botson, or however that goes, whichever one of those works for you. And there's examples on the handout in case you're trying to really understand what we're doing. All right, so let's go look at example 10. We are going to find the horizontal asymptotes. So for part A, we have 4x over 2x squared plus 1. Oh, I gotta write my y equals, or the f of x equals, either way. So I forgot to write it so y fit easier than f of x. So on these, remember, vertical was the valley. With the horizontal, it goes with the highest degree. So double H there. So y equals, we're going to figure out the highest degree. Between the top and the bottom, it is an x squared. So we're going to write x squared over x squared. How many x squareds do we have on the top? Well, we don't have any because the highest one up there is for x, so we will put 0. On the bottom, we have 2x squareds. The x squareds will cancel. You're left with 0 divided by 2, which is 0. And so y equals 0 is the line that is your horizontal asymptote. All right, let's do B. We have g of x equal to 4x squared over 2x squared plus 1. So again, y equals, x squared is still our highest degree. On the top, we have 4. On the bottom, we have 2. The x squareds cancel. 4 divided by 2 is 2. So y equals 2 is your horizontal asymptote. These do have to be in the form of y equals. It's not just equal to 2, it's a y equals 2 or a y equals 0. And then let's look at our third one. So we have h of x equal to 4x cubed over 2x squared plus 1. So y equals, x cubed is now our highest degree. On the top we have 4, and on the bottom we have 0 x cubed because we only have 2x squared as our highest. The x cubes cancel. We get 4 divided by 0. This is undefined. Remember, we can't divide by 0. So there are no horizontal asymptotes. So again, you can have y equals 0, a y equals another number, or no horizontal asymptote for our different types of horizontal asymptotes. Highest degree, match them, top and bottom, fill in the numbers, and then reduce. All right, so strategies for graphing rational functions. We're going to, again, find our y-intercept, find our x-intercepts, any vertical, horizontal asymptotes, graph what we know, and then put in any test points. All right, so this will be example 11. We have f of x equal to 2x minus 1 over x minus 1. So we're going to graph this. So the first thing we're going to do is find our x-intercept, and that's where y equals to 0. So 0 equals 2x minus 1 over x minus 1. We need to get the x's out of the denominator, so we're going to multiply both sides by the denominator of x minus 1. That gets us 0 equal to 2x minus 1, and then we'll solve for x. So 1 equals 2x, divide both of them by 2, and x equals 1/2. So we have an x-intercept of 1/2, 0. Okay, part 2. Let's find the y-intercept. That's where x equals 0. So y equals 2 times 0 minus 1 over 0 minus 1. That'll get us negative 1 over negative 1, which is 1. So our y-intercept is going to be 0, 1. All right, the next thing we need to do is find our vertical asymptote. Vertical asymptote has to deal with the value of the problem. So we're just going to take our x minus 1 equal to 0. So x equals 1 is the vertical asymptote. For the horizontal asymptote, it's the highest degree. Our highest degree on our function is x. So we've got x over x. On the top we have 2, and on the bottom we have 1. The x's will cancel. 2 divided by 1 is 2. So y equals 2 is our horizontal asymptote. So now we can graph what we know and then fill in what we need. All right, this will be part 4. Oh, actually part 5. And we're going to graph. Graph what we know. Again, we don't have really big numbers. So I'm going to put 4 hash marks on each part of our axes. So the first point we have is our x-intercept at 1/2. And we have our y-intercept at 1. And then we have the vertical asymptote at x equals 1. Vertical asymptotes are always drawn with hashed mark, never solid, and so are the horizontal ones. Well, all asymptotes are drawn that way. And then y equals 2. So we're just going to put dashed lines, but they get arrows at either end because they continue on. Now, we already have 2 points on this part. So this will just graph. Do not cross your asymptotes. Just go up near them. And then we've got to figure out what happens here. So this is what we call the test points. We have to test where the rest of the graph goes. Now typically it's going to land up here, go opposite of that, but not necessarily always. So we need to test it. So we only have to do 1 test point. You can do several if you want to, but you're just picking a point, an x, and finding the y. So we need to go past the vertical asymptote so we can find out what happens to the graph here. Is it up here or is it down here? So I'm going to go to x equals to 2, and I'm going to plug that into our function. So 2 times 2 minus 1 over 2 minus 1. Just plugging it into our original function up here. So that gets us 4 minus 1 over 2 minus 1, which is 1, so that'll get us 3. So that tells me when we are at x equal to 2, we are at y equals 3, so we're up on that part of the graph. So then I'm just going to graph this part up here. I just need to know if the graph lands up here or if it lands down there. And that's all you have to do on that one. So test points are where you test to see where the graph lands. All right, let's go look at another graph. We're going to go look at example 12. So we have f of x equal to 2x over x squared minus 4. We're going to do the same steps. First one, x-intercept, y equals 0. So 0 equals 2x over x squared minus 4, multiplied by the denominator on both sides. So 0 equals 2x, divide by 2, 0 equals x, so our x-intercept is going to be 0, 0. Okay, let's go find that y-intercept. Y-intercept is when x equals 0. So y equals 2 times 0 over 0 squared minus 4. So this will get us 0 over negative 4, which is still 0. So our point will be 0, 0. Our third step will be to find our vertical asymptote. Again, it's the value of the problem. So x squared minus 4 set equal to the 0. This again is difference of squares. So x minus 2, x plus 2 equals 0. X minus 2 equals 0. X plus 2 equals to 0. X will equal 2 and x will equal negative 2. So we have 2 vertical asymptotes this time. Part 4 will be our horizontal asymptotes, and again that's the highest degree. Our highest degree of our function is squared. So y equals x squared over x squared. On the top part of our function, we have 0x squared, and on the bottom we have 1. 0 divided by 1 is 0, so y equals 0 is our horizontal asymptote. All right, next part is going to graph. Again, we don't have really large numbers to graph here, we just have a little bit more to graph. So I'm going to do 4 hash marks again. And graph what we know. Our x and our y-intercepts were the same point. We have 2 vertical asymptotes, one at -2 and one at 2. And then our y-intercept is at 0. So if you ever have this on an exam, and it's hard to see going across, make sure you go past the graph that's on your chest so that I can tell that you knew that the horizontal asymptote was there. All right, so we're going to need more test points this time because we only have 1 point. We have to know where the graph lands here. Does it go up here or down here, up here or down here, up here or down here? So we're going to have to do a couple of test points. So our x and our y. So our vertical asymptote is at -2, so we're going to go with -3. Then we'll go with -1. Then we need to do 1, and then we'll need to do 3. So we have to do 4 test points to figure out where the graph lands on each one. So we're going to do the same thing we did on the previous graph. We're going to plug in these values into our original function. So 2 times -3 over -3 squared minus 4. So I'll get us -6 over 9 minus 4, which is -6 over 5. Which is going to be the same thing as like a -1.2. When we plug in -1, we will get 2/3. 1, we get -2/3. And at 3, we get a +6/5, which will be +1.2. All right, so our first point with our -3, -1.2, we're at -3, and what we find out is it's at -1.2, so it's going to land down here, which tells us that this part of the graph will do that. At the -1, it's a +2/3. At a +1, it is -2/3. So that tells us that the graph will kind of curve like this. Kind of like a cubed kind of situation. Not quite, but kind of. And then on the last point, we have +3 is at +6/5. So it'll be a little past 1. So that tells us the graph will do something like this. Now these are just sketches. You just need to be able to sketch what the graph looks like. All right, and then we have a word problem, and it'll be example 13. So for example 13, we have a company that manufactures snowboards, has fixed costs of $200 a day and total costs of $3,800 per day at a daily output of 20 boards. Write an equation for the cost function. Find the average cost function, which is C of x is equal, or C bar, there's a bar over it, of x is equal to the C of x divided by x. And then we're going to sketch the graph with our domain going from 1 to 30. All right, so let's write down the important parts. Our fixed costs are 200. Our total costs are 3,800 per day when 20 boards are made, and we're going from 1 to 30. All right, so for part A, we need to write the C of x function. Remember, our C of x is equal to mx plus b. B is going to be our fixed costs, but we've got to figure out what that slope is, what that m is. So to find m, we have a total cost of $3,800. That's our total. The total cost includes a fixed cost. If they say the costs or the variable costs, then we know it's just the variable part. But they told us the total cost. So first thing we got to do is subtract out the fixed cost. That gets us $3,600 for the variable cost. So subtract out the fixed to get your variable. Now, we take the $3,600 variable cost and divide it by the number of boards, because they said for 20 boards. 3,600 divided by 20 is 180 per board. So now that is going to be our m. Okay? All right, so C of x will be equal to 180x plus our fixed costs. So that's our cost function right there. Now for part B, we were asked to find the C bar of x, which is our C of x over our x, which is 180x plus 200 over x. So that's what the function is, and that's what we're looking for right there, this part right here. And that's the average cost. So it's average because you're dividing by however many you make. So it's the average of it. And now what we're going to do is sketch the graph. All right, so now that we have a fraction, because we're sketching the average cost function, we have to worry about a horizontal asymptote. So if we look at the horizontal asymptote, remember it's going to be y equals, and the degrees are going to match. The highest one is x, and on the top we have 180, and on the bottom we have 1. The x's will cancel, so 180. So y equals 180 is our our horizontal asymptote. All right, so now what we're looking at, we could also find our vertical asymptote. Let's go ahead and find that so we can kind of apply that into our knowledge. If we wanted to find the vertical asymptote, we take our denominator, set it equal to 0. Our denominator is x, so x equals 0 is our vertical asymptote. So that'll kind of tell you why we're going to land in the first quadrant in our graph. All right, so we've got to have some kind of points. We know the asymptotes, but we don't really know a whole lot more. We know that our values go from 1 to 30. That's our domain right there, 1 to 30. So let's find some values. We have x, and we're going to do C bar of x. So I'm going to put that instead of just y. So we're going to use the 1 and we're going to use the 30. When I plug in 1 into our equation, we're going to get 380, and when I plug it into, plug 30 in, we'll get 186.67. I can show you how we plug that in. We're just plugging it into the C of x function. We're plugging in 1, and then we plugged in 30. Okay, and you can just plug that straight into the calculator if you want to. All right, so that gives us our points. So let's graph this. We don't have a lot of points on our graph. We do have an example of it on your handout, so you'll be able to see what it actually looks like in your handout. But we need to know how to do these without always having the picture given to us. So this will be our x, this will be our c bar of x. We don't have a lot of points. We know we've got 0, and we're going to go out to 30. And we have a few points going up. We know that we need y equals to 180. So I'm going to do like 100s. So 1, 2, 3, 4, 500. So these are in increments of 100, just so you know. And our 1 and 380, so that'd be 1, 2, 3, 4, and 500. At 380, we are at 1. So about something like that. And at 30, we're at 187, let's say. And before we mark that, let's go ahead and do our 180, our y equals 180. So this would be our horizontal asymptote. We just got to make sure that 187 lands above 180. And we're only graphing to those 2 points. So it's not going to have arrows, and it's not necessarily going to be a straight line. It's going to be kind of a curve. It probably curves a little bit more than that, and I could find out how much it curves by plotting a few other points. You can kind of see on our handout, it does have a little bit more of a curve going on as it goes towards that horizontal asymptote. It says, what does the average cost per board tend to as the product increases? So when we first start out at the first board, it's $380. But as we get towards 30 boards, what happens to it? Well, the cost goes down towards that horizontal asymptote of 180. So for part D, the cost goes down towards the horizontal asymptote of 180. So something like that will work. It does not have to be an exact answer on exactly the way that I word it. You just got to describe what's happening with the graph.